but they have an accordion-shaped bottle that can expand, because as you have this hydrogen peroxide, it breaks down naturally over time into water plus oxygen, and the oxygen expands. And if you don't have an expanding type bottle, it will explode over time. That would be bad.
That's why you don't have 100%.
Right. Yes, you would not want to have 100%. So what we're going to do is a catalyst. It's not working, right?
It is working out, and so when you do the experiment, do you need me to move it to show it?
Well, just saying, what was wrong that got it to?
She had to check the SD card and she fixed it.
She put a different one in there probably, or?
She said it just said to check it, so I don't know.
Well, I checked it, took it out, put it back in, and we did it several times, it didn't work.
Just hanging out.
I'm just curious. Well,
So
it's
do you
working.
need me to work the camera?
No.
Okay.
No problem.
Okay, thank you.
It's recording now, right?
Yes, sir.
Okay. Slow. Now, so this is called hydrogen peroxide. The blue in front was what was needed to balance it. If you have a catalyst used, you write it over the arrow, showing that it speeds it up because of the catalyst. The catalyst we're going to use is yeast. We have some packages of yeast here. And so if you take yeast and add it to warm water, and you hit really, and then we're going to add it to the hydrogen peroxide. Now when we add it to the hydrogen peroxide, we're also going to add some of this soap. That's just, because what happens is, when this bubbles up, if I just do this without adding any soap to it, you'll see that it'll bubble rapidly, because the oxygen is being released. It's just oxygen, but oxygen is flammable. It also is exothermic. It releases a lot of heat. So we're going to take a little splint, start on fire, stick it in there when this is happening, and you'll see it turn bright light during the experiment. It didn't say to do that, but that's what we're going to do when we do it. We're going to watch some videos to explain it, this whole, what's going on in this lab, but the basic idea is that this is a natural process of decomposition that happens slowly over time. The catalyst makes it happen faster. You may have seen these kind of materials that harden. You need a hardener, like there's glue, and you've got two parts to it. When you mix them together, it happens faster. Hair, coloring for hair often has two different parts. When you mix it together, then it's going to, before you put it in your hair, it's going to make the whole process happen faster. You can't just put the colored part that's already dark, let's say it's, for me, it'd be dark brown or black, and put it in your hair. It's not going to do much good. It takes time. You wash it out. So those are all examples of catalysts that you guys are probably familiar with in everyday life. A catalyst is something that just makes the process happen faster. It doesn't change it. It enters in and comes back out. So I've done a catalyst experiment where we had hydrogen peroxide and mercury dichromate, I think it's called. It's a little bit, it's black. So I put it in there and it starts going, foaming all over, and you get rid of all your hydrogen peroxide, is gone. And you're left with something in the bottom. You can keep on adding hydrogen peroxide to that again and again and again, because that catalyst never gets used up, because it's entered into and then leaving it out. And it just gives it separate steps that I can take these steps and get there faster. And any kind of a process, we're going to look at a video that'll talk about this, but hopefully it'll. So you have a couple different processes. You have something like this, and draw another one over here. And this chemical reaction is a little different. I'm going to try to make the activation. So the activation energy is going from here to here. And that's basically breaking down it works better if you have two compounds over here. Breaking things down, what you're starting with on your left-hand side, which is a reactant, breaking those molecules down. And then, when it reforms new molecules, you have release of energy when you form your products. If there's more energy released than needed to get it to break down, the whole process to start, then it's going to be exothermic. If there's less energy released than it took to get it started, it's endothermic. It'll turn cold. Okay? Instead of giving off heat as when it's exothermic. And what a a catalyst does. Anybody got any idea what it does? Because you're going to start here and end up here in both cases. What can I change to make that still happen? To make it happen faster?
You're like catalyst? So
Right, and how do you think a catalyst might work to make that happen?
It speeds up the process.
Right, but how can it do that?
Through heat or through.
This is a key, this is the activation energy, the amount of energy needed to get it to go through this process.
does it add energy to it?
Pardon?
Does it add energy to it?
It's a good guess. It's not exactly what it does. It changes the amount of activation energy. Like that. So you don't need to add as much energy to get the process to go. And so it goes faster because of that. That's basically what a catalyst does. And the key thing to remember is it goes into the reaction, reacts, and comes back out when you're done. It just makes things happen faster because there's different steps it can take to get there. If you want to climb down from a difficult, you're up in a cliff and it's pretty steep, and you're trying to climb down, and somebody else goes about this trail, you can just walk around and end up there, get there a lot faster. You're both going from where you were down to the new spot, but one way you get there a lot faster, and that's kind of what catalyst does. So I wanted to show you this. I want to make sure that this is aimed right. I didn't check that out because she did, and I hope she has it aimed right. Okay, let's see if we can turn this a little bit there. Hopefully you can see. All right, all I'm pointing out here, it's going to have trouble for you to see this, is this is the teacher pages for chemistry. And if you go underneath my picture and the first week, and each week I list some things. I don't know why this happens. It's happened before. I think the only way to do this is to make this bigger so that it can. All right. Here's the least hydrogen peroxide lab. And what I said is yeast is an organism that contains a special chemical called catalase. Enzymes have ACE in these. Enzymes are biological catalysts that can act as a catalyst to speed it up to help break down hydrogen peroxide. This means that if you mix yeast with hydrogen peroxide, the hydrogen peroxide will rapidly break down into water and oxygen. The process it naturally follows anyway, but it just happens much more quickly. The oxygen gas forms bubbles. If you soap mixed in, it's more visual because now the bubbles get captured in the soap and it really overflows. And then I can take a splint, light it, stick it in there, and you will see it light up brighter because it's oxygen. You're burning oxygen. It's pure oxygen. And the Christmas break down here says that if you click on that, that'll take you to the list of the. Let's see if it'll let me do that. Maybe it's not set well, because it should go chemistry lab. So I'll have to check, make sure that link works, because it worked. I selected the one it said, and I put it in there. I'm going to have to make sure that that works. Anyway, bottom line is, that is supposed to be a link that will take you to what you need to do over the Christmas break. And there's a list of things they want you to do. I just want to make sure you have an easy access to it. So that, I need to know.
Do you know in general what those assignments are? Like, do we have a lab, or is it just?
Good question. I'm going to have to look it up and see. That's next week. I don't have it, but next week I know I need to produce a link. I was just showing it to you this week. So that over Christmas break, you're ready to go. Okay. So that's a I have a PowerPoint here I wanted to look at. But let's look at the video. Decomposition reaction, definitions, and examples. And I think that's it right here. Now you're going to be able to watch this and actually, again, at home and do the quiz that's with it. Sometimes it does this. sure why I had that trouble. I think I have too much things going on in my lesson later.
Process by which the atoms of one or more
That's weird.
substances are rearranged to form different substances. There are many types of chemical
Just pause it.
reactions. These reactions are often classified by
Let's
what
see.
they form or what happens
Good.
during the
Just
course
pause.
of the reaction. A decomposition reaction is a type of chemical reaction in which a single compound breaks down into two or more elements or new compounds. These reactions often involve an energy source, such as heat, light, or electricity, that breaks apart the bonds of compounds.
That's the
A
activation
simple way
energy.
to visualize a
Activation
decomposition
energy.
reaction is to use generic terms. Let's pretend we have discovered an elusive compound with the chemical formula Az. This means the compound is composed of an imaginary element A bonded to imaginary element Z.
Or
If we have a reaction equation that says Az yields A plus Z,
It could be
it shows a
compound.
decomposition reaction. This decomposition reaction example breaks one compound down into two elements. Decomposition reactions can also involve large compounds being broken
Alright,
down into
it's
small
not just
components,
individual
rather
elements.
than being broken down into single elements. For example, the compound ammonium nitrate readily decomposes into dinitrogen monoxide and water. One common decomposition reaction could save your life someday. The airbags found in vehicles actually expand because of a chemical reaction. The airbags in a car contain sodium azide pellets. When this compound is exposed to a small electric current, it breaks down into nitrogen gas and sodium. This means that when your car senses an accident, a small device sends an electric current to the pellets, and they rapidly decompose, giving off enough nitrogen gas to quickly fill the airbag. Let's review. Decomposition reactions are a type of chemical reaction that involves breaking down a compound into smaller compounds or individual elements. These reactions often involve an input of energy in the form of heat, light, or electricity to break down the compounds. Car airbags are a very good example of a decomposition reaction in action.
Okay. I want to remind you that this, when you see diagrams like this, exothermic because this is larger than that, and this is endothermic. Okay, does it give off the heat or does it take in more than it gives off? Meaning it's endothermic, it's really mainly taken in. This peak right here in both cases is the activation energy. The amount of energy needed to kind of break down the molecule before they reform. And a catalyst lowers the amount of activation energy to break things down, to get it started. In general, that's what it does. They mention ammonium nitrate. See if you guys, this is not an easy one to balance. Say it breaks down to form dinitrogen oxide plus water. So let's take a look at the nitrogen, hydrogen, and oxygen molecules. How many do we have over here? On the left-hand side.
There's two. Oxygen.
2 nitrogen,
And there's two on this side.
and there's 4 hydrogen, and there's 3 oxygen, right? And how about over here?
2 oxygen, 2 hydrogen, 2 nitrogen.
And there's 2 of everything. So how can I get this to balance? I'm not going to put a number in front of this, or that I don't put in front of this, because I have to have the right number of nitrogen.
Put a 2 in front of the H2O.
Okay, so we have 4 hydrogen here. If I put a 2 in front of this, that makes 4 hydrogen and 4 oxygen. Okay? So,
No, it's two
NO,
oxygen.
3.
no, just 3, because I added 1 more oxygen. So now it's 1, 2, 3. So now is it balanced?
Yes.
And that's all there was to it. It looked messy to balance that, but it really wasn't. So the first A, Z, to break down A plus Z is not the best example because it's almost always more complex than that. You have some, these are actually a polyatomic ion and so is this. They usually stay together when they're in chemical reactions, but in this case it breaks down to form something completely different. You notice what he called this one? N2O?
Like dinitrogen.
Dinitrogen oxide.
Oh,
And it's actually dinitrogen monoxide. What you do is, you learn the prefixes, mono, di, tri, etc. And for the first element in a compound, you don't say if it's mono. So, for example, CO and CO2. You wouldn't say monocarbon because it's the first one. If it was two carbons, you'd say dicarbon. Carbon monoxide, carbon dioxide. Okay, so, but because there's more than just one nitrogen, it's dinitrogen monoxide. You don't say monooxide because there's two O's together, they just say monoxide. And this is the same thing, dihydrogen monoxide. This is water, so we normally call this. And this is just called a nitrate because that's the name of the polyatomic ion, but it would be nitrogen trioxide, yeah. And this is nitrogen tetrahydride. That's the names. Have you guys had that in your, as you're going through your chemistry books about naming them? Because we haven't talked about it yet, but it's one of those things that won't necessarily come up in labs, but we need to start learning how to do that. The nice thing is, for most compounds are covalent, and so you have to use that. But if there's a metal involved, you don't worry about it. Magnesium chloride, sodium chloride. This is magnesium, this is chloride, magnesium chloride, sodium and chlorine, sodium chloride. You just change it to I and D. Makes it easy. Because they know that this always has a 2+ charge, and this always has a 1+ charge, so you don't need to specify how many of each one, because that's the way it reacts. If you can have more than one, and copper is an example of that, the elements in the middle of the periodic table, do you remember what they call them? This thing in the middle?
transition.
Transition elements, good. Copper can have a +1 or a +2. So you have copper oxide. You can tell from this that it must be +2 because oxygen is in two columns over from the far right column, which is the halogens, and so it always has a -2, almost always. So it's 2 negative, so this must be 2 positive. So you can say copper 2 oxide. When there's more than one possible charge you have to specify it. And when there's when there's two different ones, they have another way to do it. The higher charge they can have is called ic, the lower charge is us. So this could also be cupric oxide as well as copper 2 oxide. And then if you had copper C2O, Cu2O, that has copper just a charge of 1. So it would be the same +1, copper 1 oxide. And, or cuprous oxide. So once you get, I don't want to throw a whole lot at you, but you should begin to start learning how to name it. It's not that hard. With metals, it's pretty easy. Especially if it's the first 2 columns of the periodic table. You got lithium, and bromine is just lithium bromide. They figure you know what's the charge of lithium, and you know how many oxygen it'll need based on that. And so it's a really straightforward thing. So it's Li2 oxide if there's oxygen, but you just say lithium oxide, you have to specify. Since you can have different combinations of, of compound form with nitrogen, you can combine oxygen in all kinds of different ways, you have to specify how many there are of each one. And so for what's called covalent bonding, when you have basically 2 nonmetals, they're on the right side of the periodic table in general, then you have to specify. So, anyway, just a little covering on that. I don't even know if they would test you on that, but you're in your home schooling classes, you will be tested on that in some way, because at some point. So if you ever have questions, you can ask me. Ms. Bruce, if there's time to talk about this, just come to class ahead of time, ready to let me know at the beginning of class, and we can do it. So, good. video, and I found it somewhere. Get rid of that. No, get rid of that. We just saw that, didn't we? I may have opened up more than one. There's the, this is the link that I had with it. I put it in there. This is what should, didn't work?
Did you
I did it at home, it does go to it.
Okay, good. I don't know why I didn't when I clicked it, but it should pull up this, telling you what you need to do. Watch those videos. Oh, okay, I'll turn this off. Try this again. That's what you should see. Christmas bake, watch these videos. That means you're gonna do the quizzes for them. Complete all that, it says worksheet and quizzes. And then rubric for the gas laws paper you're gonna do. They explain about this. We can talk about that next week. But that's what you'll see when you go to that. Let me see if I can find where that other video is. That's first of all, motion, mass, inertia. I don't use that anymore. I don't want to get rid of that, that's for sure.
Mr. Bruce?
Yes.
I noticed that it's an APA format, and I know that our lab reports are in APA format. However, all of our papers for other classes are in MLA format. Should we use MLA or APA? It said APA on there, it's just we've been used to writing MLA.
Probably. To be honest, I don't care as long as you're consistent.
Okay.
As long as you're consistent with that, that's all. I think it's fine.
APA is usually used in like the sciences, whereas MLA is more in English classes. It's
Okay.
very easy to do.
I just want to make sure I don't write MLA that's supposed to be like APA or vice versa. Is it okay?
Yeah, I'm gonna have to look this up again, because I,
page. It's like
Okay.
oh, well, let me look this up again. I'm sorry, we had one. I think I had to look it up. That's right, they didn't have it. Why elephant toothpaste section? I just found this one. There it is. Yeah, it's not, I remember what it said, what it's supposed to be. All right, we're going to watch this video. This is the kind of thing we're going to do. And it's going.
Why is it called Rainbow Elephants too?
Are you ready to imagine it? This one is so huge, Carl had to blow the lid off the place right on the front of the IS, the Imagination Station. Not to be confused with the ISS, but I think they might see this from space. Hey, Carl, what are you cooking up? Well, today we're going to talk about hydrogen peroxide. It's the stuff you have in your medicine cabinet, right? You pour it in a cup and it bubbles. And the reason it bubbles is because the hydrogen peroxide, H2O2, comes in contact with catalase in your skin, which breaks down the hydrogen peroxide, turns it into basically water and oxygen gas. Okay? I can say okay. Well, let me show you what happens here. So this is just a bigger scale version. This
He's not going to have soap in it first. You just see the bubbles.
over here is 35. So it's much more concentrated. I have a catalyst in here, sodium iodide. And we're going to pour that into the hydrogen peroxide just to see what happens. Okay? Sure, because it should catalyze it and cause it to break down. So I'll pour a little bit. See. Step back. Whoa. Yeah. Catalyze it all over.
And it's just all of that oxygen being released.
Alright, so we're generating heat. We generate
And made a mess with the
oxygen
table
gas
because it
there.
carries some liquid with it. We're going to do that here on the way mats up. It'll be messier than that. It'll be more like this.
Oh, it's gonna be more like this.
Dish soap. Just add the dish soap into there. I'm going to give you the honor this time, Tony.
I'm scared.
Adding the catalyst.
Not scary.
Take the cap off. I give this to you. Swirl this around a little bit. Hydrogen peroxide, soap, catalyst. Go ahead and pour it in. Let's see what happens. Just dump the whole thing in. Release the oxygen inside. And
They call it elephant toothpaste. You can see why, because
it's a giant
got that name.
blob of oxygen.
That's oxygen-filled soap
Which
bubbles.
is really cool.
No, it's like concave.
I'm going to take this one step further. Instead of doing this in a big graduated rotating cylinder. I have set up down here 6 flasks, which taper near the top. And what I'm hoping for here is that, I'm going to do it for a while. What I'm hoping here is that as we generate this gas, it is going to generate some pressure, and inside each of these flasks, we should get a jet of foam shooting out. Okay? But one more thing. Everybody knows Reggie Div, right? Right. We're going to go the rainbow color. We're going to go the rainbow color. So we're going to add some rainbow colors here. Now, I'm a little concerned about that foam. Might have a catalyst here with dangerous. We're going to see if anything, nothing. Gingerly pour. Gingerly pour. Okay, so I'm going to add the food coloring into this one. We got a red. I'm going to let you add the next one. I'm going to take the next. And Sarah Gulch down here is going to help us with the others. So Sarah, we're just adding food coloring. We've already got the soap in there. And this is a generous pour of food coloring. Probably more than you'd ever have.
Orange, yellow, green, blue, violet.
Okay, I think we're all set up. Now, you saw what happened with that ball of foam. You're probably not going to want to put this microphone, which is pretty expensive. Set it down. Be careful of that. Sure, we each have 2 catalysts. We're going to do a little countdown. You're going to take 2 catalysts and you're going to pour quickly into there, okay? Before we do that, I just want to go over the basics. If you're heading on down to the Imagination Station, here are the hours on your screen. They are downtown, of course, at One Discovery Way. And if you look at Lucas County, kids getting free with paid adult admission. That's kids 12 and under. Now we're about to set down the microphone so we can conduct this experiment. We're going to talk really loudly as we do so. Let me hand these to you. Okay, thanks. Do the hand off. All right. Hang on 1 second. Let's get you. I have mine ready. Once we do this, there's no stopping. This is a one and done. One and done. This is the only shot. Sarah's got 2. You've got 2. All right. They're a little bit. They'll top me off there. Top me off with extra catalyst. Okay, we'll get rid of that one. All right. Okay, set down the mic now. All right. Okay. So here we go. Elephant's toothpaste. 3, 2, 1, pour.
And you see what I call it rainbow.
Oh, whoa.
All right. So,
Isn't that cool?
again, 35% hydrogen peroxide. We're using sodium.
We're not using that strong.
Oh.
Not going to react that way, as fast.
Oh, we can do
It's just a class A. It's a really
Yeah.
take a look at the ground too here. Hopefully this will be cleaned up by the time we get down on the Imagination Station. I'm sure a little rain will come by and clean all this up. We'll come out with some water.
All right, now, we're going to do the lab, and after we've done the lab, I have some more I wanted to talk to you guys about. I'll just show you what I want to talk about. We're going to just open this up. There. Chemical reactions, a little bit about chemical reactions, the energy we talked about, we talked about if it's exothermic, endothermic, activation energy and that. So I thought we would talk a little bit about that because I think it's important that we cover that. So we're not going to do that right now. We're going to get set up with our lab. So can you go down, why don't you go down and see if we can get every one of these to make sure we have enough to cover.
I don't think this is a really good idea.
This is probably, you can probably use this just this one, but I might, and here's what we're going to use. We're going to do it in a bucket, so it's going to overflow. Now, you can probably just do a load here. Here's what, you can do a turn, move that so that, let's move it all down here.
Yeah, I was about to say, because this cannot move from here.
Oops. So Gavin can see what we're doing. All
Hi,
right.
Gavin.
Hi, Gavin.
Yes.
I missed
All right.
We're
Here's what
missing
you're
Gavin.
going to do. In a cup, there's other cups here. You got 2 groups here. And then
We'd be concerned if it overflows and it's...
Guys, you don't have that much soap, so you don't want to overdo that. But you're going to put your hydrogen peroxide. This is probably better because it hasn't been opened, so I think
Can we move this
we're
forward
going to
some
open
so
up
the
this
camera
one that
can't
hasn't
see
been
it?
opened just because it'll be more hydrogen peroxide in there.
A little bit more. More. A little bit more. A little bit more.
Oh my god.
Just a little bit.
Guys, I have
Okay, there we go.
4 of these. I figured that was enough because there's, if we need, I guess we can put on another, just one per group that I thought. But anyway, that, I have one for myself. So you don't need really the safety glasses. You want a half a cup of 6% hydrogen peroxide. Okay? So estimate it, but you're gonna fill this up about halfway, each one of these, with hydrogen peroxide. There's no hurry, I mean, it's no problem, it's not gonna break down very fast.
Do we?
Oh. Yeah, one job. Okay.
And you can actually just take the top off and pour it in, you could have, but you're. Okay. And a separate container, we're gonna mix in, you got a 16-ounce soda bottle, okay? You're gonna put that in the soda bottle, you're gonna put that in your, here. Here's a couple of them. You're gonna pour that in here. Right in there, yes, and the other one in one of these. And this one's going to be sitting up in your tub. And you may want to pick up the camera so they can see it when we actually do it, because it's. That's good. There we go. Go ahead and put these, pour those to you guys. Try to do it over the. So if it spills in the bucket.
Okay, I'm not going to spill the drop personally.
And
You guys good? You guys got this? You got this.
I have faith in y'all.
this is a race to see if you can do it faster without spilling a drop.
Quality over.
No!
Ladies and gentlemen.
All right. Put them in the buckets.
100%.
Now, what you're going to do is you're going to take, we're going to have to be ready to go with the mats. Let me get another one of those.
Who wants to play with fire?
Yes.
I would like to.
Another flint.
Mr. Burrs, I like your shirt.
You like what?
I like your shirt.
Oh, my shirt? Why am I wearing this shirt at this time? Here?
Exactly.
I have no idea.
It's 20 degrees.
My mom got mad at me. Like, she actually got mad because I came down one day in shorts, and she's like, "Go upstairs and shake." I'm not going outside.
Remember the coldest day we had last year, how cold it was? Purposely, a guy comes down there in a short sleeve t-shirt and in shorts, just plain old shorts, not, I mean like running shorts.
It was like.
He's acting like he's at the store and acting like he didn't even notice it. Oh, I'm used to it because I'm from Minnesota. I'm thinking, yeah, you're just showing off. There's no
Lots of
way.
boys
that's
do that though. I feel like
almost-
lots of
yeah.
boys wear shorts
All
all
right,
the time.
so each one of you have a split, each one of you, let me get
I
another
think we should
box.
pull this
Max,
closer
you ready
since
to
we're gonna
go?
have to like actually think. Okay, JK, we're coming back this way.
Oh my goodness.
Okay, guys,
Because
listen up. You're gonna put the
Then we can,
one
like-
packet of catalyst and get some water put in here, kind of warm, not real hot. Fill it up about halfway, each one. You guys can hit your bathroom and do that. I don't think it matters if you use, you don't have to use that.
there's no warm water.
Distilled water is not necessary.
No. It's either freezing cold.
What's the time is, I don't.
It takes like
It is
11:15.
Good. You got 25 minutes.
I like my elephant toothpaste green.
So we're gonna mix that in the water, and then
It's platinum.
before you do anything, guys,
It's yeast.
you're gonna add food color. You pick your color, to give it color, into the, what you already have there, the hydrogen peroxide. So pick your colors, there's red, blue, green, yellow. If you want purple, you need to mix red and blue,
That
right?
purple did not look purple.
So you're gonna go ahead and add that, add the color you want to the hydrogen peroxide.
Does anybody want a green toothpaste?
It's a
Green
green
toothpaste? Green toothpaste?
Okay.
Well, just, let's use toothpicks. I got toothpicks. Those are too long. I don't want to waste them.
How many drops are you putting in there?
A lot. Just dump the whole thing there.
Really?
Wait, so Mr. Burrs, how much do we put in there?
A lot.
Before I like dump the whole thing?
Oh shoot, I put like a.
No, just put a few drops in. Here's a toothpick for mixing this. And go ahead and they need to do theirs.
Yeah. Girls need to do their,
Wait, that was one drop.
Now,
Okay, so we just.
has anybody ever made bread? Homemade
Yeah, we did
bread?
it
the
last
ones that
year.
learn how to.
You did it in class?
We did a lab last year when we had to like.
Yeah, we didn't make bread.
We put yeast in that. That was fun.
That was
Yeah.
weird.
And so mix it up.
We lost.
Now, you're also going to add a little bit of soap to your hydrogen peroxide.
Let's go. Come on.
So, I don't know if you want to take it out when you do it, but plenty of soap. So I'd say a teaspoonful or so. That's probably good. You go ahead and do it to the other. Now when you mix it, it's going to foam all over. What I want you to do is to verify that it's really oxygen by taking a match and lighting it. And you can stick the match in there. Remember, there's a lot of heat made, it's exothermic. So you can immediately catch this flint on fire. You could probably start it ahead of time and just stand there holding this, and then when you stick it in, you'll see it go bright. So at that point, I'll probably be holding the camera so he can see. Hello? So, do you guys understand what you're going to do?
So you're just gonna pour that in there?
Before you do, you're going to light your flint. Somebody take that one over there. Go ahead and strike the match on it. And you guys same thing. And you have a flint also, right?
I guess. I'm really good at doing matches, so I'll say this first.
So go ahead and light the match and then light your flint. Yes, it's okay. I've done it in the past. I just wanted to make sure.
No, don't do it towards yourself.
Do that.
Oh my gosh. You're
Yeah.
Dang, are you like...
Now, catch it, and it'll burn a while, so that's the nice thing. You guys do the same thing, and then somebody get ready to pour it in, and I'll get the camera so they can see it.
Like, it's fine.
Come on, friction.
Come on, guys. I'm burning here. I'm burning here.
All right, quickly, pour it in before his finger.
Guys.
There you go.
Oh, that actually worked. Where does it go? Oh, there.
Okay, go ahead and mix it in there before it goes out.
There you go.
Okay, the other person, somebody grab the cup and pour it in
Doesn't matter if it overflows?
quickly. You know, it doesn't matter. It's going to overflow.
Oh, but I didn't.
Dude,
But I did.
Did it work? Did anything happen?
It's working. Slowly.
It's going.
Oh, this
So if it had hydrogen peroxide, a higher concentration, it would work really fast.
So do I stick it in now?
Well, once it comes to the top, once you get yes, where you can see the bubbles. Is it turning brighter when you did that or not?
It went out.
I think the flame is a little.
Okay, go ahead. Stick it in there.
We need another one of these.
Oh. No!
Yeah, we'll try it again.
Well,
Let me just try a match because I've done this before. And it's hard to get it to really, because it goes out so fast, the liquid puts it out.
Oh gosh.
Somebody hold the camera so maybe they can see.
Plenty of opportunities.
Oh, I saw it like.
You heard it, spit and everything, yes.
I heard it.
This part would work better if it was a more violent reaction, so that then if you had a higher concentration of hydrogen peroxide, like 30% instead of 3. Well, okay, that part didn't work too well, but it does. There is oxygen there, and that's what we were trying to do, was to prove that that was actually oxygen, because it burns faster in oxygen. If you got more bubbles, then you put it in, it's actually oxygen there, and it goes, gets real bright.
Wait, does it work with yours? Should we try theirs?
You were too confident.
Still.
Do you not trust me?
It's okay.
There we go. Should I try it with yours?
Another one. Oh, you got.
Wait, come on.
Try it just near it, not quite sticking it in. Does it burn brighter when you get near it?
Yeah.
Hold
For
it
like
up.
a half a second.
See that? Did he see that?
Blow it, please. Please. I don't have anything on.
It burns brighter. Try it again. When you bring it near it, it burns brighter, showing that there's
I'm
oxygen.
doing this.
I know, it's really hard to get to light.
Yuck.
Use this
All right.
thing with 50
So somebody do a match, and
Ooh, first time.
now stop burning. Go ahead and hold it near it, and watch what happens when you get closer to it. Suddenly it burns brighter when you get closer to it. I don't know if you can tell.
That's not working.
What happened now?
It like expands. It's great.
It almost
Yes.
burned me. It was great.
Oh, mine did too.
Watch your fingers.
See it
You
burning
gotta like
brighter?
blow it quick, because otherwise it's gonna expand.
Okay, now watch down for it, please.
So, like I said, if you had stronger hydrogen peroxide, it'd be bigger bubbles. When you can actually go inside the bubbles, the whole thing you see catch fire in there.
You know
So what if I were to drop it into there? Would it?
Yeah, what would happen if you
just
drop
go out?
You can try that.
Can we?
I don't think it'll be a problem. I don't think.
It will
The
go
last
because
thing
that's
said before we.
Can we-
burn
That,
the
the thing is warm.
Can we try this?
Come on, you got this, you got this. I want you to go in there.
Oh, it just.
It just went out.
It just went out. Okay, now what we need to do is take this and pour it down the toilet and flush it. Don't leave it there.
Yes.
We got this.
Oh!
And when you come back, we'll do a little bit more, a little
Actually,
bit more
I was gonna say, no, you
teaching.
wouldn't.
no, I actually wouldn't. Hold on.
I just kind of want to light the mattress. I'm so disappointing.
So I'm still I was like, hold on. It might
I
be.
dare you to do it.
I'm gonna try the other side of it. Ah!
Gosh, why do I keep breaking them? Why is it?
Let it get like pretty big and then put it
You
in
might want to
there.
pull your mask down.
Ah.
See, I keep breaking them when I light. I don't know. It's because I'm so strong. It just snaps.
Joshua, you're so
You're
strong.
going so aggressive at it. You're like.
I don't know.
I just want to lay on the mattress.
All right, guys, go ahead and clean up our mess that I'm trying to get done.
Do you want me to take one of these? I'll get this.
What I wonder is if those bigger bubbles down there,
How do
if
I-
you'd be able to stick those.
Yeah, I was gonna say,
bigger
Yeah.
How do I dunk this down the toilet? Should we dump this
Try.
outside?
Just, pardon?
Should I dump this outside instead?
Well, it's gonna make a mess outside, whereas you can flush it. It'll be
It was
okay.
warm.
Yes, it is warm. That's a good point.
Oh.
It's exothermic, so it is warm and it's messy, but it's not that
Also
warm.
because we've been
Alright.
sticking fire in it.
I'm gonna figure out how to dump this down the
You
toilet.
can throw the bottle away, but if you could pour it down the toilet, that'd be good.
Okay, how do we?
Like in the big bubble.
Big bubble to the
Oh,
right.
whoa.
No, don't bite.
Oh!
Don't kill yourself.
So go ahead and pour this down the toilet, a little bit at a time, flush it, and when you come back, we're gonna go over this,
Wait a second. I just triggered myself.
I designed this for a particular level we were using, so page 268 won't work for you guys. And we go until, what time, 11:40?
Yes.
11:23, so we got about 10, 15 minutes after cleanup. I hope you were able to follow that, Gavin. And it wasn't too messy. If we had, but you can't, you have to, I have to be at a school where we were allowed to, had met all the requirements, they would order those chemicals. We could order 30% hydrogen peroxide, and it's really strong. I wonder if this is coming up well enough. Can you see? Looks like it isn't there. I don't know if that's, I guess it'd be good enough when you bring it in close on your, cover your whole screen. Where did the other one go? Here it is. So we'll start up in a couple of minutes there, Gavin. Once they clean up. So girls, if we can get going as fast as possible, I'd like that to start again.
We're trying to clean out the bucket.
I appreciate that. That would be perfect, because we just use it for waste type stuff. And it's not like, of course, it's going to foam all over, because, yeah.
We were thinking about leaving it because it kind of looked, you know, like a fun prank.
So I'm going to start in a minute, okay? All right, PowerPoint fits in perfectly with where we are. So why don't we, good, we got 12 minutes, perfect.
I don't need money.
Thank you, and, okay. So we're going to talk about chemical reaction, quantities, the idea of exothermic, endothermic, how to tell if it's exothermic or endothermic, and catalysts, what they do, etc. So, chemical reaction occurs when collision between molecules has sufficient energy to break the bonds in the reactants. You got to break apart. You see that's N2 and O2, and you're going to form NO and NO. You got to break apart the 2 nitrogen and 2 oxygen, and then each nitrogen is going to form with one of the oxygen, and so you got to break these bonds, and then you're going to form the bonds over here. That's the idea. That's why you get this hump, because it takes energy to break the bonds. And then, depending on how much energy is released, if it's exothermic, that means this is a more stable product than the original reactants in general. Now, activation energy is this part right here. From here to here, you measure this, if this is on the y-axis is energy. That is the amount of activation energy, and then this is what's formed. Would you say this is exothermic or endothermic, looking at that drawing? Right. Endothermic, right. The activation energy is the minimum energy needed for the reaction to take place when the collision provides energy equal to or greater than, because they happen to move around, happen to collide. If they collide such that they're able, with enough energy, the molecules moving fast enough, to break apart the original molecules, then it can take place. So that's why heat often makes a difference, speeds it up. Because the molecules are moving around, if they collide, it can cause the molecules that collide to break apart, and they can reform into the other elements. So exothermic gives off heat, endothermic absorbs heat, because it took more heat than it gave off. So it's going to be absorbing heat from the environment, from the surroundings. So evaporation is an endothermic process that absorbs heat and evaporates. Combustion is an exothermic process in general. And so exothermic reaction looks like a carbon plus 2 oxygen forms CO2 plus 393. Delta H, don't worry about that, that just refers to the amount of energy given off. And it's considered negative. If it's exothermic, delta H will always be negative. But the way to look at it in the reaction here is just see it on the right-hand side. It's on the right-hand side. And so therefore, you have more energy released. Okay? The energy of the products is less than the energy of the reactants. So, exothermic. Heat is a product. Here's an example. Delta H is positive, and you notice the way it's often written. The way it could be written is C plus 2H2O plus 90 dot kilojoules goes to, you would put, if the energy is on the left-hand side being added, that means it's endothermic. If it's on the right-hand side, it's exothermic. It's a product. It's given off. Okay? And it could be written as this delta H, consider a change in heat, because it's got a different name now, but originally H was used because they thought it was referring to heat. And now it's not that simple. But that's, you can think of this, the change in heat being positive. That means it needs heat to take it, so it's endothermic. If it's negative, just look at the right-hand side, it's exothermic. If the plus 90 is on the left-hand side, it's endothermic. If you compare them, you can see the difference on the graph. That's one thing you definitely want to be able to do. Endothermic, heat absorbed, exothermic, heat released. And so you find the delta, the heat, if it's shown, it's not always shown, but if it's shown in the chemical reaction on the right-hand side as a product, then it's exothermic. If it's shown on the left-hand side as a reactant, then it's endothermic. Heat has to go in to make it happen. So let's see if you can classify these as exothermic or endothermic. How about this first one? So nitrogen breaks down, hydrogen breaks down, you have two ammonia molecules formed because it's on the right-hand side. How about this guy? Okay, calcium oxide plus carbon dioxide. Is endothermic? It just says heat. It isn't specific, but it's on the right-hand side. Very good. 1, 2, 1. That's how you tell. Now, we're not going to put any details on this, but the reaction rate is how fast does the reaction take place. You can actually time it in seconds, hours, days. Some of the experiments I've done in the past in classes, we've had to come back a couple days later to see things take place. It's a slower reaction. The speed at which reactants used up or which products are formed, either way. So when you heat them up, when it's a higher temperature, they tend to go faster than a lower temperature. So some things, when you transport them, they have to be like refrigerated. And if the truck collapses and no longer refrigerated, it's dangerous because that thing can take off the reaction. So catalyst, as you can see, that's the purple line here. This one that was green at the top was what would happen in this reaction, which is exothermic. But now it doesn't need as much energy to break the molecules. Because what happens is instead of going from A to B, it goes from A to C to D, maybe to B. So, and then maybe it doesn't take a lot of energy from going to C or to D, so it ends up a shorter path. But you have to have that chemical available for it to take that path to get there. So it increases the rate of the reaction and lowers the energy of activation. That's what a catalyst does. It makes it go faster. And this activation, this one's going from like this. This has been lowered from the green to the purple. Is this overwhelming, guys? Is this making sense? Okay. And it's not used up. That's a key thing. A catalyst is not consumed. It's not used up during the process. Okay? So kind of a learning check. Increase the temperature. Does that make it go faster or slower or no change? Oops.
Not any answers.
One, it does increase. I didn't want to make them all come up at once. Removing some of the reactants. Yeah, it's going to, because it's going to just take longer for all of it to go. How about adding a catalyst?
Increases.
Placing the reactant flask in ice. Increasing the concentration of one of the reactants, stronger, more of it. That's going to increase. So they're all 1, 2, 1, 2, 1. So those are the kinds of things that can affect the reaction rate. And we'll go on. Indicate the effect of each factor listed as far as increase, decreases, or none. Carbon monoxide plus oxygen form carbon dioxide. Now, if you raise the temperature, how about adding oxygen?
I would say decreases.
It increased because it said you increase the amount of reactant. Adding a catalyst.
Increases.
lowering the temperature,
Decreases.
and that's all there is to it. Okay? So, in general, if you have more reactants, you're going to have more collisions, and therefore it's going to go faster. Higher temperatures, more collisions because the molecules are moving faster as you raise the temperature. And adding a catalyst lowers the energy of activation. That's kind of a good summary of, I think it worked well for the recording. So you can go ahead and take it. I think we are done. Thank you guys. And
Okay, now I gotta go to the next one.
Throw the matches away.